First, we're going to go over why we use a t-distribution when estimating a mean as opposed to estimating a proportion. The reason we do this has to do with the standard error of the sampling distribution. Let's look at an example to represent why we have to use this distribution for means and not for proportions. Suppose we took samples of size 10 for a distribution of sample proportions. So imagine our first sample, we took 10 observations, and for a second sample, we took 10 observations. And imagine in both cases, our successes for the first sample was 4, and our successes for the second sample was also 4. Again, nothing crazy happening here. If we were to find the sample proportion, well, that would be 4 over 10, which is 0.4, and the sample proportion for our second sample would be 4 over 10, which is 0.4. So if we were to find the standard error for our sample proportions, it would be 0.4 times 1 minus 0.4 over our sample size. We'll notice both of these samples yielded the same standard error. Let's try to do that same exact thing for means. Imagine we took a sample of size 10 and another sample of size 10. Suppose they both yielded the same exact sample means. The sample mean of our first group was 4, and the sample mean of our second group was 4. Now the question is, well, what happens to our standard error? Well, our standard error looks at our standard deviation over the square root of our sample size. Well, what's our standard deviation? Well, if we think about it, imagine we had a mean of 4 for our first group and a mean of 4 for our second group. The observations in the first group could be far away from 4, but the observations in our second group can be close to 4. They both have sample sizes of 10. They both have sample means of 4. Yet if we were to calculate the standard deviation or the standard error, average distance from the mean, you can see the first group has a very big standard deviation in comparison to the second group. So your standard deviations would change even though you have the same sample size and the same sample mean. That was not the case with proportions. If we had the same sample size, same sample proportion, we always ended up with the same standard error. This extra variability associated with estimating a mean is why we have to use a t-distribution. Right? That t-distribution accounts for that variation, which does not exist when estimating a proportion. We talked about how we don't know the population standard deviation, and thus we have to use the sample standard deviation to estimate that. What we'll find is the more observations we have in our sample, the better estimate we're going to get. What we'll find is the more observations we have in our sample, the better estimate our sample standard deviation will be to the population standard deviation. What this will result in is the closer our t-distribution will become to a normal distribution. As our sample size increases, our estimate of the population standard deviation is going to get better and better. There's going to be less variability with our estimate as we increase our sample size. Thus, this t-distribution will become closer and closer and closer to a normal distribution. If we remember the formula for our sample standard deviation S, what it did was it found the average distance an observation was from the mean, or it tried to estimate the average distance an observation was from the mean. So we took each observation, we saw how far is it from the mean, we summed up those square distances, and then we divided by the quantity n minus 1. That was that funky quantity that we used. And what this represents is a concept called degrees of freedom. Degrees of freedom. And essentially it represents how many observations are we using to estimate our population standard deviation. In this case, we're using n-1 observations to estimate our population standard deviation. Our t-distribution depends on that degrees of freedom. Remember, the more observations we have, the better estimate we're going to get of our population standard deviation, and the closer your t-distribution will be to a normal distribution. Now, it's important to keep in mind, though, that there's not like one t-distribution. You can think of it as like an infinite amount of t-distributions. For each degrees of freedom that you have, it's going to look closer and closer to a normal distribution because your estimate of sigma is going to be better and better. There's going to be less and less and less variability associated with your estimate of sigma. Let's look at now what a t-distribution looks like in comparison to a normal distribution. If we look at our distribution calculator, the distribution on our left is a normal distribution, and the distribution on our right is a t-distribution. Sometimes you'll see it referred to as a student's t-distribution. In our normal distribution, we'll notice we're in our z-score world. The mean is 0, standard deviation is 1. So if we were to input and find the central 95%, our empirical rule says we should be about within 2 standard deviations in each direction. If we wanted to be more exact, we should be going 1.96 standard deviations roughly in each direction. And we can see it visually being represented by these blue lines. This is positive 1.96, and this is negative 1.96. And the area contained between those two values on our z distribution, our standard normal, is 0.95 or 95%. Now let's do the same thing for a t-distribution. You'll notice nothing is displayed for our t-distribution until we give it degrees of freedom. This represents how many observations are we using to estimate our population spread. And so if we were to input 10 degrees of freedom, that means our sample size was 11, and our degrees of freedom therefore would be 10. So once I input that, you'll notice it too looks like a bell-shaped distribution. Well, it is a bell-shaped distribution, but it looks like a normal distribution. Just because you have a bell-shaped distribution doesn't mean it's normal. Watch, if we were to do that same thing, find the central 95% on a t-distribution with 10 degrees of freedom, notice in this case, we have to go roughly 2.23 standard deviations in each direction. We have to roughly go 2.23 standard deviations in each direction. As we increase our degrees of freedom, so let's change this to 50, and we look at that central 95%. Now we only have to go about 2.01 standard deviations in each direction. Let's change our degrees of freedom to 100. If that was the case, now we only need to go 1.98 standard deviations in each direction. If we did 1,000, we only have to go 1.962 standard deviations in each direction. 10,000, you can kind of see what's happening now. 1.960 standard deviations in each direction. We're getting closer and closer and closer to a normal distribution because our estimate of sigma is getting better and better and better. There's less and less variability associated with that estimate as we increase our sample size. So now you can see how a normal distribution and a t-distribution are related. And when we estimate a mean, and when we don't know the population standard deviation, which is essentially 100% of the time, we're never going to know that, we should be using this t-distribution to account for that extra variability that was not present when we estimated a proportion.